So is my screen visible?
Yes, sir.
Yeah, okay. Is my presentation visible?
Yes, sir.
Yeah, okay. So okay, so we have four major types of drug target. The first type is proteins. Second is the receptor. Third is sorry, I'm sorry. Okay, so we have four important classes of drug target. The first class is the protein. The second class is DNA, RNA. The third class is lipids. The fourth class is carbohydrates. So these are called as the major drug targets, right? So if we talk about protein, we have different types of protein molecules, say enzymes, okay, receptor, uh, ion channels. Ion channel is again kind of receptor, okay. So transporter. So these are different types of proteins, which can be used as drug target. Okay, so specifically, we are learning about the receptor. So the main function of receptor is basically these receptors are embedded in the membrane. Okay, so if this is the lipid bilayer, so these receptors are basically embedded in the membrane. Okay, so since this is present in the surface of the cell, okay, so the messenger molecule present which present outside the cell will come and bind to the binding site which is present in the extracellular region of the receptor, and this messenger carries some message, and that message will be transferred, right? So this messenger is called as first messenger. Okay, so messengers are basically endogenous ligand molecule that binds to the receptor and activates or inactivate the receptor. Okay, so basically we can classify this receptor into four superfamilies, and this classification is based on the function. That is what we have discussed in the previous lecture. So based on the function of the receptor, we can classify the receptors into four superfamilies: superfamily 1, superfamily 2, superfamily 3, and superfamily 4. So these are the four superfamilies of receptor. So this classification is purely based on the function. Okay, so further we can classify this superfamily 1, 2, 3, 4 into different subtypes based on the receptor, right? So I am not going to discuss about that in this lecture, right? So these are very general endogenous ligand molecule which act as messenger molecule, right? So adrenaline, acetylcholine, noradrenaline, muscarine, nicotine, right? So these are well-known neurotransmitters which act as a primary messenger. Meaning is that these are the molecules which act as a ligand, goes and bind to the receptor and activates or inactivate the receptor, right? So primary or first messenger, as I said, this is the first ligand molecule that is present in the extracellular region that goes and bind to the extracellular region of the receptor and activates or deactivate the receptor. Those endogenous ligand molecules are called as first messenger, right? So this is what we discussed in the previous lecture. So we can classify the receptors into four superfamily. Superfamily type 1, which is called as neurotransmitter. Okay, the endogenous ligand molecule is a neurotransmitter. All the ion channel which comes under superfamily type 1. So the example of fast neurotransmitters like NACHR, GABA receptor, glutamate receptor. So these are some of the receptors which comes under superfamily type 1, and the endogenous ligand molecule for this superfamily is fast neurotransmitter, right? So almost all the ligand molecules which I'm showing here is an example for fast neurotransmitter. So general structure we already discussed, right? So the N terminal used to be present in the extracellular part, and the C terminal of this ion channel also present in the extracellular region, right? So both N terminal and C terminal, they present in the extracellular region. and normally 4 to 4 5 transmembrane helices we can see, right? So I think already I discussed the structural feature. Okay, so the second superfamily is called as GPCR, or G protein coupled receptor. So the endogenous ligand molecule for GPCR, or like hormones, slow neurotransmitters, and example for the receptors which comes under superfamily type 2 are muscarinic acetylcholine receptor, nor adrenergic receptor. So these are some of the receptors which comes under the superfamily type 2. So the general name for this superfamily is GPCR, or G protein coupled receptor. Again I repeat, superfamily type 1 is ion channel, and superfamily type 2 is GPCR. Okay, so coming to superfamily, okay, so the general structural feature of this superfamily type 2 GPCR is all the GPCR proteins used to have 7 transmembrane helixes. So sometimes they are called as 7 TM. TM refers for transmembrane, 7 transmembrane helixes. The number is constant for all the proteins that belongs to GPCR. N terminal used to be present in the extracellular region, and C terminal in the intracellular region, and just below the intracellular region. So there is used to be a domain called as G protein coupling domain. So this is the place where the G protein will come and bind, right? So we'll see the mechanism shortly. So coming to the third superfamily, it is the example for this superfamily is insulin receptor. Okay, so the general name of this family is tyrosine kinase linked receptor. Example is insulin receptor. So insulin receptor is an example for tyrosine kinase linked receptor. So the endogenous ligand molecule for this receptor, or like insulin, growth factor. So these are common endogenous ligand molecule for superfamily type 3. So the important structural feature is that it used to have only one helix, or the transmembrane region. Here you can see, it's not like the superfamily type 1 or superfamily type 2. Another specialty of this superfamily type 3 receptor is that, so these are the proteins used to have two types of function. They act as receptor, and secondly they also act as enzyme, right? So the enzyme activity is present in the intracellular region. That's the specialty of superfamily type 3. Okay, so coming to superfamily type 4 is very special, because this is the superfamily which is not present or embedded in the transmembrane protein, which is present inside the nucleus. Okay, that's a specialty. So this protein is not embedded in the membrane. Okay, it's not a transmembrane protein which is present inside the nucleus. So the C terminal used to be present inside the nucleus, inside intracellular region, as well as the N terminal also present in the intracellular region inside the nucleus. Specialty of this protein is that it used to have a DNA binding domain. Okay, because these are the proteins which control the transcription translation process effectively, and the endogenous ligand molecules are like steroid hormone, thyroid hormone, vitamins. Okay, so these are some of the endogenous ligand molecule that activates or inactivate the superfamily type 4 receptor, right? So we'll see the more detailed mechanism of each superfamily. So superfamily type 1. Okay, so generally these are called as ion channels, right? So there are so many ion channels which are present in cell. You can find many number of ion channels, right? So if you ask a question, what is the need for ion channel, right? So normally if the molecule is charged, say for example you have some drug molecule which is charged, right? So the charged molecule cannot easily enter into the cell through the passive diffusion. Passive diffusion is the very common mode of entry of any molecule inside the cell. uh, okay, so if the molecule is charged, definitely the molecule cannot use the normal passive diffusion. It needs some kind of alternate method or mode for getting enter into the cell or leave the cell, right? That is why we have a special type of entry through a protein called as ion channels, right? So ion channels are the proteins which facilitate the entry of the molecule, or which can also facilitate, any molecule that has to be leaved from the cell if the molecule is charged, right? So this protein is a membrane embedded protein. Already we discussed about this, right? So the specialty of this is structural feature is that it used to have 4 to 5 membrane spanning subunits, right? So the literal meaning of this 4 to 5 membrane spanning helices are like, so if you assume that this is the membrane, cell membrane, so this family of protein used to have exactly 4 or 5 transmembrane helices, okay, which are interconnected through the loops. Okay, so if you look at each of this helix, okay, so how many number of amino acids can be present in each helix? So approximately 20 to 25 amino acids in each helix. So if you take this helix, 20 to 25 amino acid. If you take the second helix, again 20 to 25 amino acid. Third helix, 20 to 25 amino acid, and so on, right? The speciality of this is that if you take acetylcholine receptor as an example, okay, so acetylcholine receptor is made up of different subunits. So 1, 2, 3, 4, 5. Okay, so it is having 5 subunits. So okay, this is an example for acetylcholine receptor. So in the bottom you can see the description for this image. Okay, so this is N acetylcholine receptor, right? So what you're seeing here is the graphical abstract illustration of N acetylcholine receptor. The proposed mode of action of this receptor is so since it is having 5 subunits, okay, so alpha chain, beta chain, alpha chain, gamma chain, and delta chain. Okay, so I am talking only about acetylcholine receptor as an example. So this will vary from one receptor, one ion channel to another ion channel, right? There are certain ion channels which can be activated with the help of only one ligand molecule. So there are certain ion channels which need 2 ligand molecules for its activation. So one such ion channel is the acetylcholine receptor, right? So here the top view of this ion channel is this. Okay, so here you can see a gap, right? So this is exactly the opening of ion channel, right? So normally it used to be in closed state. So whenever the acetylcholine molecule, assume that this red color dot is the acetylcholine. Okay, so whenever 2 molecules of acetylcholine, okay, the first acetylcholine, if it goes and bind to this alpha chain, and the second acetylcholine, if it goes and bind to the another alpha chain. So, okay, sorry, this is not alpha. Okay, second acetylcholine, if it goes and bind to the alpha chain, second alpha chain, right? So 2 alpha chain. If 2 alpha chains are occupied by acetylcholine molecule, okay, the closed form of the ion channel, say this is the closed form of the ion channel. If 2 acetylcholine molecule binds to the alpha chain, what happens? So it makes some conformation binding of this molecule to the alpha chain, which lead for some conformational change in the protein. Okay, that lead for opening of the ion channel. Now you can see the ion channel is open because of the binding of the 2 acetylcholine molecule, right? So because of the opening of the ion channel, now here this is the closed form. Okay, so once 2 molecules of the acetylcholine binds to this, conformational change takes place that lead for opening of the ion channel. Now the ion channel is open, right? So now what can happen is that the charged drug molecule, which cannot enter through the passive diffusion, now it can enter using this ion channel. Okay, even though it is charged, since it formed a gap, so now it can get access into the cell, or the molecules which are present inside the cell can also come out of the cell. That depends on the type of ion channel, right? So this is the general molecular mechanism of superfamily type 1. Is it understandable?
Yes, sir.
Is it understandable?
Yes, sir.
Yes,
Okay,
sir.
yeah, okay. So So how many ligand molecules needed for activating the acetylcholine receptor? How many ligand molecules are needed for activating the acetylcholine receptor?
Two, sir.
Okay, so
Two.
how many chains are there in acetylcholine receptor? How many subunits or chains?
Five, sir.
Okay, so what are they? What are the subunits which are present in acetylcholine receptor?
Two alpha,
Mm-hmm.
beta, gamma, and delta, sir.
Yeah. So what is the endogenous ligand molecule which activates acetylcholine receptor? What is the name of the endogenous molecule which activates, which goes and bind to the alpha subunit?
Acetylcholine.
Acetylcholine. Okay. So what is the main job of superfamily type 1? What's main job of superfamily type 1? What's the main function of superfamily type 1? They act as ion channels. Okay. Superfamily type 1 is ion channels. So coming to superfamily type 2. Okay. So what is the structural feature of superfamily type 2? So mostly single polypeptide chain. Okay, so this is the general architecture of superfamily type 2. So this is, let us assume that this is the cell membrane. Okay, so superfamily type 2 is also membrane embedded protein, transmembrane protein. So normally, the architecture of the superfamily type 2 is used to be 7 transmembrane helices, say 1, 2, 3, 4, 5, 6 and 7 transmembrane helices. Okay, so all the transmembrane helices are joined through some loops. Okay, this is a general architecture of superfamily type 2, and the general name of superfamily type 2 is GPCR. Okay, G protein coupled receptor. So if you take the total length of this yeah, if you take the primary sequence of this GPCR, they used to have a single polypeptide chain of 400 to 500 amino acid, right? So first point. Okay, first major difference if you compare with superfamily type 1. So superfamily type 1 had many number of subunits like alpha, beta, gamma, delta. Okay, but in case of superfamily type 2, it is a single polypeptide chain of 400 to 500 amino acid. Okay, so it's a single polypeptide chain, only one chain, only one subunit. First point, right? So second point is that in case of superfamily type 1, there used to be 4 to 5 transmembrane helices. Okay, but in case of superfamily type 2, the number of helices is constant for all the protein belong to this family, that is 7. That is why it is called as 7 transmembrane helices. That is what I put up here. 7 transmembrane subunits, right? So if somebody say that a protein is having 7 transmembrane helix, definitely we can say that the protein belongs to a family called as G protein coupled receptor, most probably, right? So if you take each helixes, okay, so if you take each helixes, so there used to be 25 to 25 amino acids, okay, that forms each helix, right? The first helix, if you count the number of amino acid, may range between 20 to 25. If you count for the second helix, may range from 20 to 25 amino acids, right? So N terminal is present in the extracellular region. Okay, so if we assume this as the extracellular region, so N terminal is present here, and the C terminal is present in the intracellular region somewhere here. Okay, so coming to the mechanism of GPCR is very important for examination point, right? So there are, because if you look at the pie chart of disease causing protein molecule, GPCR plays a very important role, right? So more than 60% of the drug target is it belongs to some GPCR protein, right? So coming to the detailed molecular mechanism of GPCR, right? So let us assume that this gray color region is the illustration of the receptor, and this gray color circle is the ligand molecule. Okay, so this is the transmembrane region. Okay, this region is the transmembrane region. Okay, this protein is embedded in the transmembrane. Okay, so it's a membrane embedded protein. So architecture is we should have 7 transmembrane, right? So all the 7 transmembrane regions are illustrated as one single gray color box, right? So we know that so the ligand binding domain is present in the extracellular region. This is the extracellular region and this is the intracellular region. The ligand binding domain is present in the extracellular region. So what should happen? The endogenous ligand molecule should go and bind to the ligand binding region of the receptor. So we know that this ligand molecule is the primary messenger. Okay, many times we discussed this. So it carries a message and that message should be transferred to the receptor from intracellular to from extracellular to intracellular, right? So this second image, it's the illustration of binding of this. It's a bound state of the receptor. So because of binding of this ligand molecule to the receptor binding site, what happens? There is a kind of conformational change. Here you can see. So here there is no gap here, but after the binding of ligand molecule to the binding site, you can see some kind of gap here. Okay, this is what I mean here as the conformational change. Okay, the reason for this conformational change is the binding of ligand molecule to the receptor binding site that lead for the conformational change. So if you ask a question whether the conformational change is taking place in the extracellular region or the intracellular region, so definitely the conformational change is taking place in the intracellular region. Okay, the conformational change that takes place in this region of the intracellular part of the cell, intracellular region of the cell, which attracts a small protein molecule which is floating inside the cell called as G protein. The G proteins are very small protein molecules. It's not a big protein, it's a very small protein molecule which is made up of 3 subunits: alpha subunit, beta subunit and gamma subunit. Okay, again I repeat. So G protein is normally present inside the cell. It's a very small protein molecule which is made up of 3 subunits: alpha subunit, beta subunit and gamma subunit. So to this alpha subunits, okay, there's a chemical which is attached to this called as GDP. Okay, so you might already studied about GTP, GDP and all, right? So there is a chemical which is directly attached to the alpha subunit called as GDP. So now this entire G protein is attracted to this position because of the conformational change that takes place due to the binding of the ligand molecule. Is it understandable?
Yes, sir.
Okay, so what's the reason for the attraction of G protein towards the receptor?
Conformational change in the
Conformational change in the intracellular region of the receptor. Okay, good. So because of the conformational change, it attracts this. Okay, because of the attraction, it goes and bind. Okay, it goes and bind. So this image is the illustration of the bound state of G protein to GPCR receptor, G protein coupled receptor. Okay. So here you can see this protein is now attached to the GPCR successfully. Okay, after this attachment, what happens? This GDP will be converted into GTP. Okay, this GDP converted into GTP, right? So the difference is one additional phosphate group will be attached to this. Okay, so because of binding of G protein to the GPCR lead for the conversion of the chemical change from GDP to GTP. Hope understandable, right? So here you can see the GDP is now converted into GTP. Okay, so because of the conversion of GDP into GTP, now this G protein is highly unstable. Again, I repeat, very important for examination point. So the conformational change lead for attraction of G protein. So G protein goes and bind to this position. Good. So immediately because of the binding of G protein to GPCR, the GDP which is attached to the alpha chain of G protein is converted into GTP. Okay, one additional phosphate is added. So because of addition of one additional phosphate group, because of the conversion of GDP into GTP, what happened now? This system is highly unstable. The system is highly unstable. And what happened is that, so this alpha subunit with the GTP, this alpha subunit with the GTP dissociate from the beta and gamma. Okay, so here beta and gamma is still in its complex form, but the alpha subunit with this GTP is dissociated. The alpha subunit with GTP is dissociated. Okay, is it understandable?
Yes, sir.
Now this system, it can act as a secondary messenger. Okay, so what it can do, it can go and bind to some other ion channel. Already we discussed what is ion channel, right? So how the ion channel is activated, right? So even through GPCR, the ion channels can be activated. The alpha subunit with this GTP, it can go and bind to some superfamily type 1 receptor ion channel, and it can activate the ion channel, or it can inactivate or deactivate the ion channel. Or the alpha subunit with this GTP, it can go and bind to some enzymes, and it can activate the enzyme or it can deactivate the enzyme. So anything may happen, right? So we can say that this alpha subunit with GTP is good example for secondary messenger, which can either activate some events inside the cell or it can deactivate some events inside the cell. Example: activation of ion channel, inactivation of ion channel, activation of enzyme, or inhibition of enzyme. So these are the things that can be done with the help of the secondary messenger. Is it understandable?
Yes, sir.
Okay, so now, so after executing its job, the alpha subunit with GTP. Okay, again, what will happen? This GTP will be converted into GDP. GTP will be converted into GDP, and it goes and attached to the beta and gamma subunit. So finally, this G protein will be recycled. Again, I repeat. So the dissociation takes place because of in the conversion of GDP into GTP. Okay, so the alpha subunit with GTP dissociate from beta and gamma subunit. Still, we have the beta and gamma subunit as the complex. So the alpha subunit with the GDP execute its job. Okay, either activating the ion channel or inactivating the ion channel, activating the enzyme or inhibiting the enzyme, whatever it is. After some time, the GTP attached to the alpha subunit will be converted into GDP. Okay, so that conversion will again lead for attachment of alpha subunit to the beta and gamma subunit, and we'll get back alpha, beta, gamma subunits with GDP, that is the G protein. The meaning is that the G protein is recycled here. Is it understandable?
Yes, sir.
So again, what will happen? This G protein, so whenever the ligand bind to the GPCR and induces or activates or induces the conformational change, will attract this G protein. Again, the same thing will happen. Okay, so this is how the signaling takes place in case of GPCR. Is it understandable?
Yes, sir.
Okay, so that is the basic general function of GPCR. Okay, so coming to superfamily type 3. So superfamily type 3 is called as tyrosine kinase linked receptor. Okay, so already I told the example is insulin receptor. Okay, insulin receptor is an example for tyrosine kinase linked receptor. So the special structural feature of this superfamily type 3 is they used to have single helical transmembrane subunit. Okay, so if you assume this as the transmembrane region, if you consider this as the lipid bilayer, right? So it used to have only one single transmembrane subunit. Okay, so if we compare this architecture with superfamily type 1 and superfamily type 2, so superfamily type 1 is 4 to 5 transmembrane helixes, type 2 is constant 7 transmembrane helixes, type 3 it used to have single helical transmembrane subunit. Okay, this is speciality of this. So as I said that it has two function. One is it acts as a receptor. So we know the function of receptor is receiving the information from outside of the cell and transferring that information inside of the cell. So it does the job of receptor. Also it has another function called as it's having the function of enzyme. Okay, this is the only superfamily which has the enzyme function in the intracellular region, right? So okay, so we will see the general mechanism of this superfamily type 2. So this is the single transmembrane domain. Okay, single transmembrane helix of superfamily type 3. So here we have the ligand binding domain. Okay, so this is the extracellular region and this is the intracellular region. So in the intracellular region, okay, so this region is having the enzymatic activity. The enzymatic activity of this superfamily type 3 is not present in the extracellular region, it is present in the intracellular region, right? So the structural feature is it's having only one transmembrane helix. So the ligand binding domain is present in the extracellular region. These are common points, right? So once okay, so here you can see it is represented as OH, right? So which means that those are the places in which we have some amino acids having the side chain OH. Okay, so I hope that you know what are the amino acids which are having the side chain as OH. Okay, so say tyrosine, right? So if you take serine, right, these are the some of the amino acids which are having the OH group, right? So in this specific case, these are the tyrosine amino acid, right? So tyrosine is nothing but the side chain is a phenyl ring to which OH group is attached, right? So you have to understand that we have many number of tyrosine residues here because the name of this receptor is tyrosine kinase linked receptor, right? So this OH which illustrates the side chain of tyrosine. Is it understandable?
Yes, sir.
Yes, right. So what happens? The binding of the ligand, okay, to the ligand binding domain, which is present in the extracellular region, that lead for dimerization. Very important for examination point, right? So this is the first case in which the binding of the ligand, which induces the dimerization of the protein. Okay. So again, I repeat, the ligand molecule bind to the binding pocket of the receptor, which lead for dimerization. What is meant by dimerization? The single unit of the protein is now converted into two units. Two units joined together. That is what is called as dimerization. Dimer is two. Monomer is one. One monomer unit, because of the binding of the ligand molecule, is now converted into dimeric form. Is it understandable?
Yes, sir.
Okay, so we can say two monomer units joined together because of the binding of the ligand molecule, right? So because of this dimerization, right? So which lead for uh, this tyrosine, right? So this tyrosine OH. Okay, so because of the dimerization, what happens is this tyrosine OH side chain of the tyrosine is phosphorylated. Okay, so here you can see the OH is now replaced by P. Okay, So scientifically, the meaning of this conversion is the OH group is now phosphorylated. Okay, so this is the OH is phosphorylated. Here the OH is phosphorylated. Here the OH is phosphorylated, and here the OH is phosphorylated. Okay, so the dimerization which lead for phosphorylation of the tyrosine residues which are present in the intracellular region in the tyrosine kinase domain. Is it understandable?
Yes, sir.
Yes, right. So because of the phosphorylation, now this attracts, okay, some of the protein molecules which are having a very specific domain called as SH2 domain. Okay, so again I repeat. So because of the phosphorylation, right? So this phosphorylation, so in case of GPCR, we said that the conformational change that lead for the attraction of a protein called as G protein. Just like that, the change of the tyrosine into its phosphorylated state that lead for attraction of a protein having a specific domain called as SH2 domain. There are some protein molecules which has a domain called as SH2 domain, and those proteins are attracted towards this phosphorylated tyrosine kinase residues. Is it understandable? So this is a protein having SH2 domain that is attracted towards the phosphorylated state of tyrosine kinase domain. Is it understandable?
Yes, sir.
So what happens, this because of the binding, because of the attraction of this SH2 domain, okay, to this phosphorylated state of tyrosine kinase, so it activates the enzyme system and transcription, various transcription factors which lead to the cellular response. Okay, it's a very general mechanism. Again I repeat, the binding of the ligand to the uh, receptor binding site lead for dimerization of this protein. The dimerization of this protein lead for phosphorylation, autophosphorylation of tyrosine kinase residues which are specifically present in the tyrosine kinase domain. So because of the autophosphorylation of tyrosine kinase domain, which lead for attraction of proteins having a very specific type of domain, SH2 domain, and because of attraction of that protein to the tyrosine kinase domain, lead for activation of different enzyme systems and transcription factors. Okay, so which lead for cascade of cellular response, and that is the general molecular mechanism of the superfamily type 3. Is it understandable?
Yes, sir.
Okay, so superfamily type 4, I just leave it to you, right? So because that's a very simple superfamily, right? Architecture is simple. It used to have only there is no transmembrane helix in it, right? So it is not membrane embedded protein molecule. So it is completely present inside the nucleus. Okay, it mainly controls the transcription translation process. They used to have a DNA binding domain. I just leave it to you for reading on your own. Is it fine?
Yes, sir.
Okay, so in the next class, what I'm going to do is that I'll give some real-time example of what are the GPCR which are involved in causing disease, and what are the drug molecules which are used for ion channel GPCR and some other protein types. Okay. So looking at the syllabus, I hope you have the syllabus with you, right? So so let me show the syllabus, right? So
So I just want to know, have you read that article to some extent? Have you gone through?
we'll see where we are.
Yeah, right. Because yeah, he's a chemist. Dr. Rambabu, he's a chemist. So
Is the syllabus visible?
And he's now involved in
Yes, sir.
working in
Yes, right. So
what is that?
so what we understand is that
Development of that is compounds that could
So receptor
target
proteins,
all
ion
systems
channels as
more
drug targets.
interested in
Okay.
this field.
Receptors and diseases, right? So what we have to discuss in the next lecture class is mechanism of drug that affects cardiac function, vascular system, lipid lowering drugs, right? So this part I can finish comfortably, right? For this part I'll be giving the recorded version of the lecture, okay, for the last unit, because last unit is very simple unit. It won't take more than 3-4 hours for you to finish the fourth unit. Is it fine?
Yes, sir.
For the entire fourth unit, I'll be giving you the recorded version for the entire fourth unit, right? So it's a very simple unit, right? So it won't take more than 2-3 hours for you to prepare, right? So in the next 3-4 days, we will comfortably finish this part, right? So how many quizzes over?
Actually, this interest was in biochemist, something like in a chemistry journal. Let's move to critical reviews and microbiology. Okay. The reason is
How many quizzes over so far?
and, it would be easy also for us to get published. Yeah, I think it's more than 7. We already have a paper.
2, sir.
Only 2 or 3?
This paper also to get published there. Okay. So the idea could be like the very first part of that review.
Assignments are also part of quiz.
Start with what exactly bacterial infection.
How many we completed so far? 2 or 3?
Sir, 2 quiz and 1 assignment, sir.
Yeah, 3 totally. Okay.
Yes, sir.
Assignment is also part of quiz. Okay, 3. So we will have only 3 more. Okay.
Message image.
So maybe this week we will have 1 more. Okay.
We have to show an image like that. Yeah,
Okay, sir.
Okay. Yeah. Okay. Any doubt I can address. Otherwise, we will wind up the session.
Mouth you will have different players. Infection first.
See, for the examination point, I'll give some question bank for you. Okay.
How exactly bacteria could evade a host?
Also, I'll give some needed materials.
So either few first address.
You can very comfortably take the final examination. There won't be any issue. Okay.
So the final examination will be on.
Okay, the final examination, the question pattern is 10 2-mark question. And the mode of examination is, as of now, they have planned you to come here and write the examination. Okay, you have to appear for the examination in person. It's not online examination. Okay. So the question pattern I have given for this paper is like 10 2-mark question. And you'll be having you had to write 15-mark question. One second.
So இந்த விஷயம் நீங்க தான் திங்க் பண்ணணும். சோ இத நம்ம ஃபர்ஸ்ட் அட்ரஸ் பண்ணிட்டு அப்படி ஸ்லோவா மூவ் ஆகும்போது ஓகே இது ஒரு சீரியஸான விஷயம்னு தெரியுது. சோ கன்வென்ஷனலா இத எப்படி நம்ம டார்கெட் எப்படி ட்ரீட்மென்ட் பண்றோம் இந்த டிஃபரண்ட் போஸ்ட் நீச்சர்ஸ்ல நமக்கு ட்ரபிள் கொடுக்கிற இந்த பேத்தோஜென்ஸ் how we are tackling with the current conventional treatment அப்படின்னு பார்க்கும்போது டெஃபினட்டா ஆன்டிபயோட்டிக்ஸ் டாமினேட் பண்ணும். am I right? yeah so அந்த இடத்துல ஒரு டேபிள் நீங்க கொண்டு வர வேண்டியதா இருக்கும். so என்னென்ன ஆன்டிபயோட்டிக்ஸ்
yeah, you have to write 4 15-mark question out of 6 and 1 20-mark question compulsory. This is the question pattern for your final examination. Okay.
Yes, sir.
Okay, so for internal marks, 6 quizzes. Out of 6, I'll take 4 best. Okay.
Okay.
For examination point, I'll tell how to prepare each unit, right? So it won't be that much difficult for you to prepare for this paper. And we'll discuss few previous question papers, right? So we'll give you some idea, right? So how to approach for the examination. And also I'll give some question bank for you, right? So all those will help you. You can get very good marks in this paper. Okay. You can get a good score. Okay.
Thank you, sir.
For important topics, we'll have very periodic revision during your study holidays. Okay.
Okay.
Okay, whatever I feel as the most important topic for examination, I will give some kind of revision periodically, even if the working day is over. Okay.
Yes, sir.
Those who are interested, they can join with me. Okay.
Yes, sir.
Yeah. Any
Thank you.
doubt I can clarify. Otherwise, we'll wind up.
இப்போ நீங்க ரைட் சைடுல பார்த்தா ஒரு இமேஜ்
Sir, we completed 3 quiz and 1 assignment, sir.
இதுல பாத்தீங்கன்னா அந்த சிக்னல்
Okay, we will have 3 more quizzes. Okay, no problem. Huh?
Okay, sir.
Okay, I'll take the best 4. I just want to favor the students always. Okay.
இப்படி பண்ணா நம்ம வந்து இது பண்ணி if so
Yes, sir. Thank you.
Yeah.
இந்த டேபிள் 2 வருது
So this week probably we'll have one quiz. Huh?
செக்ஷன் வரலாம் so
Okay.
Okay, sir.
Maybe next week we'll have another one quiz, and I'll take the best 4. That's not an issue. Okay.
types of foreign sensing inhibitor so far அது எந்த பாக்டீரியா
Maybe this weekend I'll release the mark for the first 3 quizzes. Huh?
Sure, sir.
Yeah,
Yes,
you will get an idea.
அந்த பையன் எப்படி எழுதிருக்கானா ஒவ்வொரு பேப்பர்ல இருந்து எடுக்கிறத வந்து தனித்தனி டேபிளா
So again, I tell that all the materials I'll give for examination point. There won't be any issue for this paper. Okay, you can get very good score in this paper.
we have to address
Also, I'll tell how to prepare for the examination. Okay,
அதோட டார்கெட்ஸ் எல்லாம்
Yes, sir.
very easily you can score very good mark in this paper.
so target specifica யாரு then
So any questions or shall we wind up?
like எப்படி எவ்வளவு effective concentration so toxicity ஏதாவது இருக்கா then evolution of resistance ஏதாவது இருக்கா
Okay, I think we can wind up the session. Huh?
last tableல வந்து last column
Yes, sir.
Yes, sir.
Yeah. Okay.
paperல இருந்து எடுத்திருக்கீங்க so இது
Thank you.